Surface tension. It's not something you think about often, but if you've worked with the world's most common resource, water, I guarantee you have observed it daily. In this video, we plan to go over the phenomena of surface tension. With jarringly different setups and very different visuals, we will go over each and every one of the three that we've selected. Starting out with something you will see every time you fill up a glass of water. So, the first phenomena we are going to be talking about is a meniscus. You'll see it every time you use any of the lab equipment, and as you can see, each of these glasses, as they're filled up to a certain amount, have a small indentation, where the outside ring of the water is not the same height as the inside. It is a concave dip right there. The most profound of this is the bottom right, the smallest tube. This is caused by the overall downward fluid attraction as each of the water molecules, as we'll have better examples of later, attract each other and pull the water down. However, there's an adhesion force that the water is experiencing on the outside with the glass. The smaller and smaller the glass, the more and more area that proportional to the overall cross-sectional area of the glass is touching the beaker. This causes a meniscus, where the center is the actual point you want to measure at. We can actually calculate the size of the meniscus. This is a mildly complex formula that is shown on the screen. Most of the numbers come out to a constant that we would know for any beaker, like theta is the attack angle, g is gravity, but the one thing that isn't a constant and changes from beaker to beaker is r, and that is the radius of the cross-section for wherever the top of the water is. That is why larger beakers that have a big bulb at the bottom have a small meniscus until you get to the short stem, the very thin stem at the top, and then the meniscus becomes much more profound. As the radius goes higher, the overall meniscus size decreases. They're inversely proportional. Finally, we'll see a video of capillary action when the radius gets so small that the meniscus size continues to grow higher and higher and higher and higher, that the water will actually move up on its own without outside force, as displayed in the video here.
Hi there, this is for Fluid Mechanics Lab 1. We are talking about the surface tension of water, and more specifically this example is how water can hold the weight of a needle with the surface tension. So normally all of the other water molecules in this glass are all equally attracted to each other, and so they don't move around and flow on their own, right? And so say one molecule were to be attracted to an arbitrary direction. The reason it's not allowed to do that is because all of the water molecules behind it will then be pulling it back to its original position with an equal amount of. However, on top of the water, since nothing is above those molecules to pull it that way, they are able to make stronger bonds with the other molecules on top, and that allows them to carry a bit more weight on the surface of the water. And so to demonstrate this, we have a needle, and we can get it very close, and boom, there we go. So as we can see the surface tension, you can kind of see the water bending under the weight of the needle, but it is able to float on there, and then as soon as we apply any more force, we'll watch it sink. But I'm just noticing that the tip of the needle is actually just under the water, interestingly enough. So even after it's broken the surface tension, the rest of the surface tension on the surface of the water, or holding up the rest of the needle, is still enough to keep it afloat. And we'll just tap it and watch it sink.
Alrighty, the last demonstration of surface tension that we're going to be going over is going to be beading and droplet formation of water. We've already covered cohesion and hydrogen bonds and how water likes to gravitate towards its center of mass. We've primarily done this using water in some kind of container or a enclosed environment. But what if we had water not in a container? It was just sitting there, just water by itself. You'd have this drop of water here, and it would pull close towards itself all around. It would create a near sphere-like shape. And here I have a video showing this. As the water is dropped down, you can see that it's maintaining like a semi-dome shape, and it's gravitating towards the center. And you're also seeing the droplet formation as that water leaves the needle here, that the water continues to stretch and stretch and stretch as it's gaining mass until the surface tension can no longer support it. So that would be beading and droplet formation.